Good morning, I am Sheetal from Basic Chemistry Honors second year. Today I am going to make an audio recording for visually impaired student. Topic is Diazonium salt. Introduction. Diazonium salt discovered by Patrick Grace in 1858 constitute a very important class of aromatic compounds having the general formula ArN2 positive X negative where X may be anion such as chlorine, bromine, HSO4 negative, NO3 negative, BF4 negative, etc. The name diazonium itself originated from the fact that these compounds contain two nitrogen atoms, French azoid is equals to nitrogen, and resemble ammonium salt in certain respect. It may be pointed out that aliphatic diazonium salt, it means the compound having the N2 positive X negative group attached to an alkyl radical are too stable to be isolated. Structure. The simplest and the most important diazonium salt is benzene diazonium chloride. Let us first consider the structure of this compound as a representative of structure of diazonium salt in general. The important evidence leading to its structure may be summed as follows. First is molecular formula. Its molecular formula is C6H5N2Cl. Second is observed behavior. It is colorless crystalline solid soluble in water but insoluble in organic solvents such as alcohol and ether. Second, it undergoes ionization in aqueous solution as shown by the conductivity measurements of the solution. Thus, benzene diazonium chloride exhibits salt-like behavior. Third is it undergo many substitution reaction in which N2Cl group is replaced by monovalent groups such as halogen cyanide, etc. Fourth is it undergoes coupling reaction to form azo compounds such as p-hydroxyazobenzene. Fifth, on reduction with stannous chloride and HCl, it is reduced to phenylhydrazine C6H5NHNH2. Sixth, in alkaline solution, it forms salt known as diazoids, which exhibits geometrical isomerism and exist in syn or cis and anti or trans form. Third is earlier formulae. First, scientist is Gray's formula. The earliest structural formula for benzene diazonium chloride was suggested by its discoverer Patrick Gris. In this formula, the two nitrogen atoms were directly attached to the benzene nucleus as shown below. However, this formula was immediately rejected as it could not account for following properties of benzene diazonium chloride. Its salt-like character. Second is its reduction to phenylhydrazine which contain only one nitrogen directly attached to benzene nucleus. Third is the displacement of N2Cl group as a whole in most of the reaction. Fourth is the formation of azo compound in the coupling reaction. Second is Kekule formula. Kekule proposed the following structure in which only one nitrogen is directly attached to the benzene ring. This formula could explain most of the reaction of benzene diazonium chloride, but it failed to account for salt-like behavior of benzene diazonium chloride. Second is instability of benzene diazonium chloride as compared to azo compounds since both contain nitrogen double bond nitrogen linkage. C is Bloom-Strand formula in its modified form. Bloom-Strand suggested that the following structure for benzene diazonium chloride. This structure has now been modified as supporting evidence. The above ionic structure, which is comparable to the ammonium chloride, is supported by the following observation. First is benzene diazonium chloride is soluble in water but not in organic solvent due to its salt-like structure. Second is the conductivity of aqueous solution confirm the presence of charged structure. Third is IR spectrum shows the presence of nitrogen-nitrogen triple bond. Fourth, it can explain all the reaction of benzene diazonium chloride. Fifth is it can explain the existence of geometric isomerism of diazoids. It has been suggested that in the presence of hydroxide ion, the diazonium ion exists in equilibrium with diazohydroxide, an unionized compound, and the salt derived from it is shown below. The concentration of the different species depend on the pH of the solution. In acid solution, the equilibria favors the diazonium ion, while in alkaline solution, the equilibria are in the favor of the diazoids. The diazoids can naturally exhibit geometrical isomerism and exist in syn or cis and anti or trans form as depicted below. Nomenclature. Diazonium salt are named by attaching the word diazonium to the name of parent aromatic compound. This is followed by the name of the anion. For example, benzene diazonium chloride, p-nitrobenzene, diazonium hydrogen sulfate, p-toluene diazonium bromide, p-chlorobenzene, diazonium fluoroborate. Preparation of diazonium salt, diazotization. Diazonium salt are usually prepared by the reaction between aromatic primary amine and nitrous acid obtained in situ form from sodium nitrate and a mineral acid such as hydrochloric acid or sulfuric acid at about 273 to 278 Kelvin. The reaction is called diazotation and may be represented as procedure of diazotization. For carrying out diazotization, the amines is dissolved or suspended in an aqueous solution of the mineral acid and the resulting solution is cooled to about 273 Kelvin. A well-cooled aqueous solution of sodium nitrate is then added slowly, taking care of the temperature of the reaction mixture does not rise above 278 to 283 Kelvin. If the temperature is allowed to rise higher, diazonium salt formed converted into phenol. The addition of sodium nitrate solution is stopped as soon as few drops of reaction mixture gives a blue color with starch potassium iodide paper indicating the presence of some unreacted nitrous acid in the reaction mixture. In other words, it shows the completion of diazotization. Since excess nitrous acid is likely to interfere with the subsequent reaction of diazonium salt, it is destroyed by adding a small quantity of urea. Any urea left unreacted does not interfere with the reaction of diazonium salt. The above solution containing the diazonium salt is used as such for other reaction and no attempt is made to isolate the pure salt. This is because dry diazonium salt often undergo explosive spontaneous decomposition. Furthermore, since diazonium salt decomposes slowly even in cold situation, the solution must be used for further reaction immediately after preparation. It may be pointed out that liberation of nitrous acid from sodium nitrate and the formation of diazonium salt require 2 moles of the mineral acid per mole of amine to be diazotized. But in actual practice, the amount of acid used is about 3 moles. The use of excess acid is necessary to maintain proper acidity for the reaction and to prevent the combination of diazonium salt with the azotized amine. Precautions to be taken during the preparation of diazonium salt. The following precautions should be taken. First is temperature must be carefully controlled and not allowed to rise above 283 Kelvin, otherwise a phenol could be formed. Second is the mineral acids such as HCl or H2SO4 should be used in excess, otherwise diazonium salt formed would combine with undiazotized amine. Third is excess of nitrous acid must be destroyed. Fourth is never try to prepare pure dry salt because it is highly unstable and undergo explosive decomposition. Mechanism of diazotization. It has been shown by Lockworthy that the actual mechanism of diazotization depend upon the extent of acidity and the concentration of reactant, but there is no doubt that the nucleophilic amine undergo attack by some electrophilic species such as nitrosonium ion or nitrous anhydride obtained from nitrous acid. Thus, one of the probable mechanisms which appears to operate in many cases may be summed up as follows. In the presence of strong acid, nitrous acid dissociate to give the nitrosonium ion. This ion attacks the nitrogen of the amine to form an unstable N-nitrosammonium ion in intermediate. The intermediate immediately lose a proton to form an N-nitrosamine, then in turn undergo a rearrangement by the proton shift similar to ketoenol tautomerism to form diazohydroxide. Finally, in the presence of acid, the diazohydroxide loses water to form the diazonium ion. The complete mechanism is summed up below. Aromatic amines carrying electron withdrawing substituents such as NO2 in the ring are rather difficult to diazotize. This is because the electron withdrawing substituent reduces the nucleophilic character of nitrogen of the amine and thus renders it less susceptible to attack by electrophilic species. This observation also constitutes evidence in the favor of the above mechanism. Diazonium salt containing ions such as Bf4 negative are generally obtained from the more common diazonium salt as shown below. Benzene diazonium chloride plus fluoroboric acid give rise to benzene diazonium fluoroborate. Physical properties. Diazonium salt are generally colorless, crystalline solid, freely soluble in water. Second they are seldom isolated because of their instability and explosive nature. Third is with certain metallic salt such as zinc chloride, diazonium salt form double salt which are quite stable. Chemical properties. Diazonium salt are highly reactive compound and are extremely useful as intermediate in the preparation of many aromatic compounds. By the use of diazonium salt as intermediates, it is possible to introduce onto the aromatic ring substituents which are difficult or impossible to introduce by other methods. In addition, it is also possible to introduce substituents in position not favored otherwise in direct process. The reaction of diazonium salt may be divided into two main types. These are first is the reaction in which N2 is given out and the diazonium group is replaced by some other atom or group. Second is coupling reaction in which nitrogen atom are retained in the product. As already stated, diazonium salt are employed in various reactions in the form of their aqueous solution, which are prepared just before they are required to be used. The important reaction of diazonium salt are discussed below. First is reaction in which nitrogen is lost as N2 and diazonium group is replaced by some other atom or group. First is replacement by chlorine, bromine or CN, Sandmeyer's reaction. A very important reaction of diazonium salt is the Sandmeyer reaction in which diazonium group is replaced by the chlorine or bromine atom or a cyanide group. The reaction is carried out by treating solution of freshly prepared diazonium salt with cuprous chloride, bromide or cyanide. Thus, we have p-toluene diazonium chloride in the presence of cuprous chloride give rise to p-chlorotoluene plus N2. In case of replacement by cyanide, the diazonium salt solution is neutralized with sodium carbonate before being treated with cuprous cyanide. This is to prevent the loss of cyanide as HCN. Mechanism. The mechanism of Sandmeyer reaction is uncertain. However, a probable mechanism involving free radical may be summed up as follows by considering the reaction with cuprous chloride. It appears that species such as CuCl2 negative, CuBr2 negative, and CuCN2 negative are first formed, which subsequently lose an electron to diazonium ion to yield an aryl radical, cuprous salt, and nitrogen. The aryl radical and cuprous salt ultimately react to give the final product. Gattermann reaction. In a modified procedure known as Gattermann reaction, the replacement by chlorine, bromine, or CNI is carried out by using copper powder and halogen acid or potassium cyanide in plane of cuprous cyanide, that is synthesis utility. Sandmeyer's or Gattermann reaction offer a very useful method of preparation aryl chloride and bromide in pure form. The method is preferred to direct halogenation as the latter usually result in the formation of mixture of products. Since the cyanide obtained by the above process can be easily hydrolyzed to carboxylic acid, this constitutes a good method for preparation of aromatic acid. For example, O-tolvic acid may be prepared from toluene as follows. Second is by replacement by iodide. Replacement of diazonium group by iodide can be brought about merely by warming the diazonium salt solution with potassium iodide solution. Mechanism. The reaction proceed by SN2 mechanism. I negative ion being by the attacking species and constitute the best method for introducing iodine onto the aromatic ring. Third is replacement by fluorine. Bell-Sachmin reaction. For replacing the diazonium group by the fluorine, the diazonium salt solution is treated with fluoroboric acid. When diazonium fluoroborate Ar N2 positive Ba4 negative get precipitated, the precipitate is filtered, washed and dried to isolate the fluoroborate. The dry salt on heating decomposed to yield the aryl fluoride, boron trifluoride and nitrogen. The reaction known as Bell-Sachmin reaction may be depicted as below. Mechanism. The reaction proceeds by SN1 mechanism as shown below. Fourth is replacement by OH. On warming an aqueous solution of diazonium salt, the diazonium group is readily replaced by OH to yield a phenol. Mechanism. The reaction proceeds by SN1 mechanism as given below. The aforeseen reaction takes place slowly even on allowing an ice-cold solution of diazonium salt to stand. That is why diazonium salt solution are used for further reaction immediately after their preparation. The phenol formed in the reaction can couple with diazonium salt to form azo compound as discussed a little later. The coupling reaction is however suppressed in strongly acidic solution. As such, the formation of phenol is best carried out by slowly adding the diazonium salt solution to a large excess of boiling dilute sulfuric acid. Synthetic utility. The above method is very useful for preparing phenols which are otherwise difficult to obtain. For example, M-bromophenol may be prepared from nitrobenzene as follows. Fifth is by replacement by NO2. This is carried out by decomposing diazonium fluoroborate with sodium nitrate solution in the presence of copper powder. Thus, as we have synthetic utility, the reaction can be used for introducing nitro group in specific positions in benzene ring. Refer to the preparation of p-dinitrobenzene from aniline. Sixth is replacement by aryl group, Gomberg-Beckmann reaction. Many diazonium salt react with other aromatic compound in alkaline solution to furnish compound in which the diazonium group have been replaced by aryl group. For example, seventh is replacement by arsenic acid, ASO3H2 Bart reaction. This is called out by decomposing a diazonium salt with sodium arsenate in the presence of copper salt. Eighth is replacement by hydrogen. Replacement by diazonium group by hydrogen can be best carried out by allowing the diazonium salt solution to stand in contact with hypophosphorus acid, preferably in the presence of cuprous ion. The reaction may be represented as shown below. Synthetic utility. The reaction afford a convenient method for removing an NH2 or NO2 group from an aromatic ring. The complete process involving diazotization of an amine and subsequent reduction of diazonium salt is called diamitation. This can be very useful step in many syntheses as a reaction in which nitrogen atom are retained in the product. Ninth, reduction to hyd- hydrazines, no loss of nitrogen. On reduction with reducing agents such as stannous chloride and HCl, sodium bisulfate or sodium sulfate, diazonium salt reduces to hydrazine. Free hydrazine can be obtained from its salt by reaction with sodium hydroxide. Coupling reaction. A very important group of reaction of diazonium salt involves the reaction of diazonium ion acting as electrophilic agent with aromatic compound containing powerful electron releasing substituents such as OH, NH2, NHR, and NR2. The reaction known as coupling leads to the formation of compound called azo compound having the general formula, where G is the substituent such as OH, NHR, NH2, NR2, etc. The azo compound are strongly colored compound which constitute a group of dyes known as azo dyes. The coupling reaction in general may be depicted as follows. It may be noted that the nitrogen of diazonium group is retained in the product and the reaction generally takes place in para position with respect to the substituent present on the aromatic ring being attacked. However, if the para position is already occupied, the attack occurs at ortho position. Mechanism. The mechanism of coupling involves the usual electrophilic aromatic substituent in which the diazonium ion is the attacking reagent as shown below. It may be pointed out that diazonium ion is very weakly electrophilic, that is why it can attack only very reactive aromatic rings. That is rings which contain strongly activating substituent. However, if the electrophilic character of diazonium ion is increased by introducing electron withdrawing substituent like NO2 into the aromatic ring of diazonium ion, coupling may take place even less reactive aromatic compound. Choice of experimental condition. An important factor to be taken care of coupling reaction is the choice of suitable experimental condition. The reaction condition should be such that the coupling take place rapidly and the possible side reactions such as reaction of diazonium salt with water itself to form a phenol and the coupling of phenols thus produced with diazonium salt are prevented from taking place. The most important reaction condition which requires to be regulated is the pH of the reaction medium. That this is illustrated below in case of coupling with phenol and tertiary amine. 10th is coupling with phenol. When treated with phenol in weakly alkaline solution, diazonium salt undergo coupling to form hydroxoazo compound. For example, mechanism. The mechanism of the reaction involves the electrophilic attack of diazonium ion on the phenoxide ion as shown below. Role of pH in coupling reaction. The choice of optimum pH range to be employed in this reaction may be understood in terms of respective equilibria involving diazonium ion and the phenoxide ion. It may be recalled that in the presence of OH negative ion, diazonium ion occurs in equilibrium with diazohydroxide and the diazotate salt. Both diazohydroxide and diazotates are not electrophilic and therefore do not take part in coupling. This means that in strongly alkali medium, high pH value, the concentration of attacking electrophilic species would be low. In other words, a high concentration of attacking reagent requires the solution to be acidic. Phenol in aqueous solution occur in equilibrium with phenoxide ion as shown below. Due to the stronger electron releasing effect of O negative than OH, phenoxide ion is more reactive towards electrophilic attack, but the equilibria depicted above would shift towards phenoxide ion only in an alkaline solution. Thus, a higher concentration of phenoxide ion requires the reaction medium to be alkaline. In the light of above discussion, it is evident that the optimum pH range for coupling reaction would be result of compromise. The optimum pH range for coupling reaction of phenol has to be found to 9 to 10. This means that coupling of phenols is best carried out in slight alkaline solution. Coupling with tertiary amine. Coupling of diazonium salt with tertiary amine take place in slight acidic solution to form dialkali amino azo compound. Mechanism. The mechanism of reaction may be depicted as below. Role of pH. As already explained, a high concentration of diazonium ion requires the reaction medium to have low pH value, but a low pH, the amine will be largely protonated as shown below. Now, the protonated amine due to positive charge is quite unreactive towards electrophilic attack. This means that the coupling reaction, the amine should be predominantly in free form, which is possible only if the reaction medium has a high pH value. As a result of compromise between the pH range requirement of diazonium and the free amine, the actual pH range employed in the coupling of tertiary amine is 4 to 5. The reaction medium is slightly acidic. A reaction with primary and secondary amine. Primary and secondary amine generally react with diazonium salt in mildly alkaline solution to form colorless diazomonium compound. In the reaction, attack of diazonium ion take place at amino nitrogen rather than on ring. However, the diazo amino compound thus formed undergo rearrangement when heated in acidic medium to form the colored azo compound, for example. Synthetic application of diazonium salt. Introducing the chemical behavior of diazonium salt, it was stated that diazonium salt can be employed as very useful intermediate in the synthesis of a number of aromatic compounds, many of which were difficult or impossible to synthesize by other methods. The preparation of O-tolvic acid, M-bromophenol, and 1,3,5-tribromobenzene were cited as some example of synthetic utility of diazonium salt. A few more examples are given below by way of further illustration.